Kimchi, before we started this lecture, you had a question. Can you repeat it?
Yes. For the number 6 in the lab 5 write-up, it is asking about the hydrolysis of ammonium acetate, and you need to find the equilibrium constant. And I know that they're not really different steps, but there's different processes. So I don't know what matters when you're finding the equilibrium constant of the whole thing.
Can you do the last question on lab 5 for me? Okay, so it says you want to figure out what ammonium acetate does for its dissociation, right?
Yeah.
So it says you want to look at NH4AC going back
Can you
and forth.
share the screen?
Oh, shoot, I'm not doing it. Oh, dang it. I thought I shared it. Horrible instructor. There we go. There we go. Okay. Kimchi asked, can I do the last question on lab 5 for me? And the answer is, of course I can. All right. This is actually kind of a clever, the thing I liked about all these questions in lab 5 was it took a little bit of sitting down and thinking about what is going on and how do we do things. It involves flipping things and reorganizing. And it's kind of like, for any of us who took geometry and our teacher made us do proofs, it's kind of like doing a proof.
Mm-hmm.
And so when you look at this, what you want to do is look at the equations that we already had available to us.
Right. There's ammonium going down into ammonia and hydrogen, right?
The ammonium ion, right? So you had NH4 plus going back and forth to make H plus and NH3. And that's governed by
Ka.
the Ka, right?
Right. And then I also had acetate plus water goes to make acetic acid and OH minus.
Right. And that's a Kb. Okay. So when we look at this, what I want to do is I want to switch these to match the overall reaction, because as we look at it here, okay, as we look at it here, it's not going to look like what we want. So let me point out that in this, we have the NH4 and the AC matching up here. And perhaps less intuitive is here's your NH4 AC, but they're on the wrong side.
Right.
Okay. So we're going to flip to match the above. Okay.
Okay.
So when I do that, I'm going to go ahead and let's see, you gave them to me as this. So I'm going to go NH3 plus H plus goes back and forth to make NH4 plus. Now that is the Kb, right? That's now 1 over the Ka. And I should probably note that this is for the Ka for NH4 plus, because we're going to have too many Ks floating around. So let me do this, Ka of NH4 plus, and this is the Kb for HAC. So if I flip the other one around, I'll have HAC plus OH minus goes back and forth to make AC minus and H2O. And that's 1 over the Kb for HAC. Now, as we have that, now we can start to see that we have our NH4AC, those two coming together, is making our NH4 and our AC minus. The problem is we have these waters.
Mm-hmm.
Okay. But guess what we also have at our disposal? We also have H2O, goes back and forth to make H plus and OH minus, and that is a KW. So now, Garrett, remember, we're not technically canceling out, but I do want to point out, oops, I want that undo, 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 boom. A nice little light slash through these will allow us now to just keep those pieces that we want when we get down to the overall reaction, which is supposed to be this NH4AC, which is the combination of the ammonium and the acetic acid going back and forth to make NH4 plus and AC minus. Now at the end of this, that means that we have KW all over the Ka for the NH4 plus times the Kb for the HAC.
Oh. Okay.
And so if you plug those in, you'd have 1 times 10 to the minus 14, all divided by, I think both of these are the 1.8 times 10 to the minus 5s. No, they're the 555 to the negative 10s, right?
Yeah.
Yeah.
Wait, so what happened to your HAC and your NH3 from the...
They combined, right?
Oh, they combined to make NH4AC?
Right.
Okay.
And so, and you guys know how I got this 555 to the negative 10, right? It's the 1 overs.
Right.
And this will end up being like, if I'm not mistaken, 32,400 equals the equilibrium constant for that. Now, oh, let me do that. I can circle better than that. Now, of course, if you were just to look this up, the literature would probably say large.
Yeah. Oh, that's all it says.
Yeah.
Oh.
Now, but we expect this. We expect this. Maybe not you, Kim Chi, because you weren't here for Chem 110, 120 or something like that. But we expect this. Why do we expect this? Wayback Machine, solubility rules. Who always swims?
Sodium.
Sodium, which by proxy means who else? Potentially, you can tell me?
Potassium.
There you go. Thank you, Ben, for chiming in all enthusiastically. Right. But also the lesser known one on that solubility, if you recall, is the ammonium ion is also incredibly soluble. Now take a look. Who else is always soluble? All nitrates are soluble, all perchlorates, and all
Acetates.
there you go, acetate. So we have two things here that are incredibly soluble. So it's no surprise that ammonium acetate would have a large equilibrium constant to make it go to the other side. Does that make sense?
Mm-hmm.
Now keep in mind, this is a nice, cool, fun, clever proof. I would probably not ask you something this intricate on an exam, but it is a nice little homework exercise where you can take the time and really sort of, fumble your way through these things. To be quite honest, when I started this class, the first thing I did was go through all these post-lab questions. And yeah, for a while I was like, wait, what am I supposed to do here? Until I started really thinking about what are all the tools that I have in my toolbox. And, 20 minutes later, I'm like, oh, God, that's how I get rid of this. And of course, now the answer makes sense. So, don't freak out if you're just like, yeah, I would have never got that in a million years. I mean, you might not have, because it does require a little bit of cleverness there. So, but there is the clever, and I hope it makes sense.
Yeah, it does. Thank you.
All right. Well, look at that. I just did your homework for you. Yay. Not like I didn't do almost all of lab 4 for you as well, but you know. I planned it that way actually, so. What?
Nothing.
Did somebody just say, did he?
No, I said that.
Oh my gosh. All right. All right, let's take a look then at a triprotic. I promised you this fun and merriment, and really, I like doing the triprotic because if nothing else, it's good practice for doing any and all titrations. This is going to be no different than anything else. I wonder if I can actually draw a really cool plot for you here. Oh, shapes. Get an XY. Let's see if I can draw this without without going off screen here. Boudica's going to have to help me with figuring out how to make sure everything shrinks in. My Chem 110 notes have inserted extra pages here and there, and I don't know why. And now I don't know why I have a weird cursor going on here. Stop that. All right. I'm going to attempt to do this kind of nicely here. We know on the left-hand side, we're going to have pH, and underneath we're going to have the volume of the base. I'm going to go ahead and put a little mark here. Let's see. I think I'll do it in orange. Put a mark here, here, and here. And I'm going to sketch the curve. And in fact, I'm going to put some markers out there for me, just so I don't screw it up here. Let me actually undo that just a touch. I want to come back down a little bit because I don't want it to look too symmetrical. So we know that this will plateau up, go up again, plateau off, go up again, plateau, go up again, and go over. I probably had more room, didn't I? Shoot. Let me fix that. Let me redraw that here. I'm trying to get to where okay. So what we have here, I'm going to keep sketching it out, are the 3 regions. Since it's a triprotic, we know we'll have 3 regions on our plot here. Let's not spill our coffee again today. That would be twice. I would start crying, infant. I almost did the first time, and then I realized I could make more. All right, so we have region 1, region 2, and of course, now that we have a triprotic, we have region 3. Hopefully by now you realize what these 3 sections are down here on the x-axis. This is the endpoint 1, endpoint 2, and endpoint 3. And of course, all of these are governed by M1V1 equals M2V2. Now, a couple other parts that we can point in here. The initial point over here. How do we get that initial point? How do we calculate that? Dallas, type it away. What's the equation we use to get that? Or anyone can jump in. Am I still broadcasting?
Yeah.
Okay. We're just being shy.
Is it x squared over a minus x equals ka1?
That's correct. So this is x squared over a minus x equals ka, and thankfully Kyra said 1, because we're going to be in the first region. That means on the other end, we have this point here. So Kyra, if you'd be so kind, you can give me that one.
X squared over b minus x equals kb2.
KB
3.
3. Okay. Other things that we can note in here. We have this point, and this point. What do the purple X's represent here?
Halfway point equals pKa 1, 2.
Absolutely. So this is pH equals pKa 1. We have pH equals pKa 2. And pH equals pKa 3. I'm just pointing out that as we do this, as I build this curve, right, there are so many points that we can instantly generate here. So we have this point here. How do we determine that one? pH equals?
pKa 1 plus pKa 2 divided by 2. I don't know if it'd still be 2, but.
Yep, it's still 2, which means this one right here.
pKa 2 plus pKa 3.
Yep, 2 plus 3. All right. And then all points in between, pH equals pKa 1 plus log of x over a minus x. I wonder if I can actually just copy that. Can I copy that?
You should be able to copy and paste. Go to the home.
And then can I edit it?
Oh.
Look at that. Oh man, getting savvy up in here. Oops. So as we look at this, oh, and then finally we have our over titration out here. Wow. You know, when you kind of lay it out like this, holy cow, it's easy. I think it looks kind of good. So now that we have that, why don't we go ahead and do one? And I know it, hopefully at this point, this is going to be everyone yawning on the other side of like, why are we doing this yet again? Because listen, if we can do this, we can do anything. Yes, it's going to take some time. No, I'm not going to ask you a triprotic on the exam. But I also do want to point out something very unique about, well, I shouldn't say unique, but characteristic of triprotics, which I think is important for your bio classes. Okay. Oh. Oh dear. Why is there a, what is this? Oh, there we go. It's gone. Okay. So now that we have everything all in one spot, let's do one. Let's do citric acid. We're just going to abbreviate this as H3-CIT for citric acid. And I'm going to say we have 100 mils of 2 molar citric acid. (100 mils of 2 molar H3-CIT with 1,500 mils of half molar NaOH. Just want to make sure I'm kind of in my same margins. I don't trust those margins, so I'm going to rewrite this. Ooh, I don't have to rewrite. I'm getting all professional in here. There we go. Oh, where's Tanaris? That's what we're missing. Okay. We should also note our equations here. We have H3-CIT going back and forth to make H plus and H2-CIT minus. This has a Ka1 equal to 7.1 times 10 to the negative 4. Then we have H2-CIT minus. Goes back and forth to make H plus H-CIT 2 minus. This has a Ka2 equal to 1.68 times 10 to the minus 5. And finally, we have H-CIT 2 minus going back and forth to make H plus and CIT 3 minus. This has a Ka3 equal to 6.4 times 10 to the minus 7. Is everyone okay?
Yeah.
Thank you. Okay, so taking a look at this, what's the first thing we should figure out? First of all, I'm gonna just double check if anyone had a chat in there. No, it doesn't look like it. Okay. What's the first thing we need?
The end.
The end point, that is correct. So let's get that end point. End point volume. Oops. I wonder how many oops are going to be all over these videos. M1V1 equals M2V2. And remember, we can use this because we're only talking about 1H to 1OH at every time. So it's always a 1-to-1 ratio. So we have 2 molar citric acid, and I think it was, what, 100 mils?
Mm-hmm.
And our other was half molar. And we want to know that V2. So V2 is equal to looks like 400. Okay. So as we look at this, we immediately have a whole bunch of information. What this means now is that the first halfway is 200 mils. The first end is 400 mils. The Second half is now 600 mils. The second end is 800 mils. The third half sorry about that, I had 80 instead of 800. The third half is going to be 1,000 mils, and the third end is 1,200 mils, which also means we have 300 mils over. So immediately that sort of sets our goalposts about what we need to do. And what do you think we should do for our increments here?
I'm sorry, how did you know that it was 300 over?
Well, because I told you at the prompt, it was going to be 1,500 mils. And we're ending at 1,200.
Okay.
Dallas wants to do every 25. Woo! I think we can do 50. Just because, I mean, well, technically, no. I mean, we could do 25 because let's face it, we all have the calculators. We can crank them out. It's just going to make for a long table, but that's okay.
Can we do 40?
Could we do 40? 40, 80, 120, 160, 200. Yeah, let's do 40. That's a nice little compromise there, Kyra. Not that I have to say this anymore, but because it's on video. Kyra says, how about every 40? Okay, so we're going to make a table that's probably actually going to not only just go vertical, but also horizontal. So let's see. We're going to get our volume of base and our pH. And so we're going to start out with 0, 40, 80, 120, 160, 200, 240, 280, 320, 360, 400. I'm going to go ahead and just copy this. What just happened? Let's just copy that. And that way I can keep the same interval here and just make everyone a little happier. So move everyone over. Let's make a nice little table. So this is going to be a long table. Yes, we're going to have a lot of points. Yes, we're going to have to plot a lot of stuff, but I think it will end up being useful here at the end of everything. So let's get our table up here. And we should all stay in our margins. And so adjust your table accordingly. So 400, and then we go 400. This is going to go. Erase all this. So that's 440, 500, 540, 600, 640, 680.
Did you do 440 to 500?
If you wanted, you could probably do this in
440 to
Excel and then
480,
copy
sorry.
it over.
480. I can't do math right. Sorry about that. 440. I thought there was something weird. So 480, 520, 560. Now we have our 600. 640, 680, 720, 760, 800.
Forrest,
Yeah.
you could probably do this in Excel and copy it over.
Oh, I could, but that would defeat the purpose of writing a whole bunch of stuff and working on my handwriting. 840, 880, 920. 960, 1,000, 1040, 1080, 1120, 1160, and 1200. And Chef, just because, go ahead and give me my over titration volumes that we want to use for the next 300. Actually, I'm going to give them to us first because I don't want to have to do too many calculations. Let's just go 1,300, 1,400, and 1,500. Because I'm afraid Dallas will say every 10 and we'll be here forever making calculations that actually take time. Okay, so once again, everyone, of course. Once again, I want to point out that this is going to be a big graph. It's going to be a lot of number crunching, and I'm not going to make you do something this big, but I need to point something out about the triprotics, which is why we're doing this. Okay. Whew. So now, let's go ahead and get the points that we can. Which ones do you want to get? Oh, there's some stuff here more on the chat. Well, yeah, Excel would be easier. Do you really want me to do? Well, no. I mean, I can make a chart, but what else do you want me to do there, Chad, with my Excel? Because I'll tell you, you know, the lab that we're not going to do involved you guys making a very huge Excel spreadsheet to calculate all this for you. So I guess if you wanted to make an Excel spreadsheet to do this for you, I can't stop you. I mean, it'd be good if you knew how to program in the equations. I just think you don't want to write. All right, someone said they start with the half points. Yeah, I say why not? So let's do our halfway points. I think those are going to be nice, and I believe I put those in blue. So let's do the halfway points. So the first halfway, pH equals pKa1. I wonder if I can actually take that chat thing and move it, or I can't. So hopefully that won't go away, Dal, since you got them up for us. So that's negative log of 7.1 times 10 to the negative 4. And Dal also told me that's 3.15. Second halfway, pH equals pKa2. So that's negative log of 1.68 times 10 to the minus 5, or 4.77. And then the third halfway. pH equals pKa3, or negative log of 6.4 times 10 to the negative 7, or 6.19. Chad, what do you mean they are available in Excel?
Yeah, there's various formulas, scientific formulas you can use in Excel, and then there these formulas, like, I don't know, for lack of a better word, these types of formulas are available in Excel, but that's just, like, I fully admit that I'm lazy. But yeah, you can just plug in the formula, copy paste, and it will update, and you could run the whole.
Yeah, if you know how to program in Excel, there are ways of basically making it crunch it for you. In fact, one day I was screwing around and I tried to actually make a automated triprotic acid wheeling machine where I could just plug in concentrations and volumes and the KAs and say go for it. If you're good at programming, you can do that, and I have it somewhere. It took some time though to work out all the kinks, because of course you have to worry about when does the Henderson-Hasselbalch break down, or how do you program the increments. So if you're good enough, I mean, I'll tell you right now, these are take-home things, Chad. If your tool is to use Excel versus your calculator, I can't stop you, because if you're good enough to program it, that tells me you do know what you're doing. So, you know, let's face it, that you guys will have tools, yeah, and your TI Inspire will maybe also do it if someone knows how to program it. Ben probably knows how to do all that, so Ben can probably help you. But you know, in a classroom setting, your tools are limited. You'll have a few more tools out there. I'll still write it as though you are in the classroom, just for people who aren't Excel savvy. That wasn't the point of this exam, so so don't worry. It'll still be doable with the tools you have. But if you have better tools out there, Chad, knock yourself out. You know, that's what this is about, is learning how to use any and all the tools around us to get the job done. Preface that, any and all tools except for calling up your buddy. I think that went without saying.
Yeah, no, I like to do it both ways. So,
yeah, and that's totally good. Okay, so let's go ahead. I'm going to go ahead and pin those halfways real quick up there. So we had 3.15, we had, I think, 4.77, and we had 619.
I have a quick question. Oh, okay, never mind. I skipped. Never mind. I figured out what I did. I skipped something.
Never skip, unless you're in the sidewalk and there's a little children next to you. Then it's actually fun. Never forget how to skip. Okay, now I know what Dallas would say next, but I don't want to do that. I want to go ahead and get my endpoints. If you do those last, that's totally fine. But I like pinning myself down. So let's get the endpoints. So let's get the initial point. And as we said before, that is x squared. Ooh, did I use red? I love color coding this if I can. No, I used green. Shoot. That's easy. Ready? The magic of technology. All right, x squared over A minus X equals Ka1. Now we don't have to do any fanciness on this. We don't have to do any extra calculations. So it's X squared over, what is that, 2? 2 minus X equals Ka1. Of course, Ariane is going to say neglect X. Oh wait, Ferris is here. So Ferris can stunt double for Ariana. All right. So let me go ahead and rewrite that a little bit better. So now we have X squared over 2 is equal to 7.1 times 10 to the minus 4. X is going to be equal to Dallas.
What the hell?
Dallas, you're my human calculator. So 0.0377. And Ferris, what is X? I know you're here, Ferris. I saw you. Can't hide from me. Well, actually, you can. Concentration of H plus. That is correct. I don't know why you won't talk to us. All right. So in the end of this, this means that our pH is equal to 1.42. Oh, okay. I just thought you didn't love us anymore, Rachel. Let's go ahead and plug that in. And then I'm going to double check the color I used for my endpoint. That was also green. Let's do the endpoint. And Kyra will tell me that's X squared over B minus X is equal to KB.
3.
3. Okay. Now here's where we have to do the extra little calculation. So we need B. And of course, that comes from our initial stuff. So that's 2 moles of H3 sit per liter of H3 sit. And we started out with 0.1 liters of H3 sit. And we know 1 mole of H3 sit gives us 1 mole of sit 3 minus. And our new volume, let's make sure I don't go beyond. We should make it. What is our new volume here?
It's 100 plus 1200.
Yep. So it's 1.3 liters. .3 liters of the solution. At the end of that, that means that our concentration is, I think maybe 0.154. Is that correct, Alice? My glasses don't work at range, so my notes are a little far away from me.
Yeah.
Okay. So we got 0.154, and Miss Ferris will note that that is our 3 minus. That's going to be our B. We're going to throw it in there. So now we have X squared over 0.154 minus X equals the KB3. Of course, she's going to tell me neglect X. And so now we have x squared over 0.154. We're going to convert the Ka to the Kb. So that is 1 times 10 to the minus 14 over that, that value of 6.4 to the negative 7, which Dallas has typed in there. Can you guys see what Dallas types?
Yeah.
Okay, cool. So at the end of that, x equals, looks like 4.90 times 10 to the minus 5. Dallas, confirm. And then Rachel will tell me what x is. Oh, so close, Rachel. Aha. Oh, you realized your mistake? Get it? Oh. Did anyone ever see? She's typing OH minus now, so dad joke. All right. All right, we're all big boys and girls. We don't have to actually do all that calculation to get our H plus. Let's go straight to the pH. pH is equal to 9.69. Does anyone need to show how that is? Chef, you okay?
Yeah, I'm good.
Okay. So I'm going to go ahead and put that up there.
The only thing I was a little confused on, I was thinking that would be the concentration of CIT 2 minus, but it makes sense that it's OH minus.
No, it's the CIT 3 minus, right?
Oh.
Because we're at the end.
Oh, yeah.
Okay. So we are at the end. Okay. Okay. So now we just need to get the points. Oh, what else can we get very quickly?
The other endpoints.
Yeah, the other endpoints. We could have also done that right after our halfways. So I'm going to go ahead for notes consistency. I think we could actually squeeze them in right here. No, I wrote too big. All right. I don't want these to mash pages. So, so the first end, pH equals pKa1 plus pKa2 divided by 2. So that's equal to 3.15 plus 4.78 divided by 2. And that is what do we got? 3.97. Thank you. So the second end.
5.48.
5.48. Okay. I'm just going to remind us pH equals pKa2 plus pKa3 all over 2 or 4.78 plus 6.19.
Mm-hmm.
And I'm sorry, you said that was 5.48.
48.
Okay, 397 and 5.48. All right. Let's crank through some other points. So now, first region in between. And of course, that is the Henderson-Hasselbalch. So at, so what we need there is, sorry, pH equals pKa1 plus log of x over A minus x. We need A, and we need x. So what is A again?
The volume of the acid.
Moles of acid.
Oh.
Yeah, moles of acid. And so that is the 2 moles of H3 cit per liter of H3 cit. And we said we had 0.1 liters of H3 cit. And that will give us 0.2 moles of the acid. And that is my A. Now X, Kyra said we're gonna do 40 mils. And again, just like it's moles of acid, it's moles of base. So let's take a look at that. We had a 1/2 molar solution of sodium hydroxide. And we said it's 40, so 0.04 liters of NaOH. And so that is what, 0.02? Just 1 0 or 2 zeros? It's 2 zeros.
No, it's 2.
I don't know. Someone will correct me.
I did 1 0.
It's just 1 0, okay? And I'm just doing math on the fly. That is our X. So, and I do want to point out, maybe I should do this here because I can. Nope. I'm going to put our acid in red. I'm going to put our base in blue. And just remind us that the acid will be in red and our base will be in blue. Okay.
Scroll up for a second.
Say it.
Scroll up for a second.
How far?
Never mind, I'm good.
Okay. So now we can do this at 40 mils. pH is equal to the pKa, which was 3.16. Is that correct?
3.15.
3.15. Is that what we wrote?
I think so.
Yes, it is. Okay, it's going to be 3.15 plus log of 0.02 all over 0.2 minus 0.02. Check it. And that pH will be 2.1. Thank you, Dallas. 2.19. I will do the second one just to show you. So at 80 mils, pH is equal to 3.15 plus log. Now we're doubling it, so it's 0.04. We can put those in there, and 0.2. And Dallas will tell me that's 2.55. Okay. At this point, we can say ditto for region 1.
Hey, just to clarify, you're not like doubling it every time. You're doubling the base every time, but that number you're just adding 42 each time, right? That
Do you not like that question, Chef, or how it was phrased?
Well,
Try again.
I think when you say double, it's just
So
a little.
I went from 2 to 4, right? Because I doubled the volume.
But you really
So-
just added 2 to it.
You really added.
Yes,
40.
I am adding that increment. Yes.
Okay. Yeah.
So then maybe I should back up and just for clarification, and maybe this will cement it for you. So let's see, at 120, pH is equal to, once again, 3.15 plus log of 0.06, right? Because now we're 3 times the volume.
Yeah.
Over 0.2 minus 0.06. And Dallas conveniently left that up as 2.78. Does that make sense, Chef?
Yep.
Okay. And then we're just going to say ditto. Ditto to end of region 1. So now we just need second region.
Wait, Forrest.
Yes.
The last endpoint for region 1 is, I mean, not endpoint, but the point before it is 4.1.
I know. We're going to talk about that.
Okay, cool.
This is why I did it. I know you guys are all bored and you're like, we get it. Why are we doing this? This is stupid. There's a reason why I'm doing it. There really is. And so I know that right now it looks like busy work, which is why I'm going to kind of skip to the end. For the second region, you just change pKa2. Everything else is the same. A is same. X is same. Just start over. So I'm going to go ahead and do one of those. So the first volume for the second region is what, 640?
40.
At 640 mils. Remember, that's 40 mils. Oops. That's 40 mils into region 2. pH is equal to pKa2, which was 4.78. 4.78 plus log of 0.02 over 0.2 minus 0.02. We're going back to that same increment. And remember, our pKa is what is now shifting it all for us to the new area. And so Dallas will tell me that that is did it really go down that far? Oh no, yeah, it will, yeah. 3.82. And then now we can say ditto for region 2, I hope.
This is for 440 mils, not 640 mils.
Well, then why don't you guys stop me before I write this for like ever?
I said it.
No, I didn't hear it.
Oh, okay.
Because I'm looking over at a different thing from far away,
Oh.
and so I saw the second thing, and anyway, the dangers or the hazards of learning how to use glasses. So I'm sorry about that, guys. I don't know how to do this like look over and look under type thing yet. I'm getting there. Old man can learn new tricks. Are we okay saying ditto for region 2?
Yeah.
Anybody have a problem with that? All right, so third region, everything's the same. I guess I could just do this. I hate doing this to you guys. But I'm just gonna go ahead and say, why can't we just control copy, control paste, and then drag this thing down? Right, we're just going to do this all over now, but now for the third region. Third region is just the same. Just change it to pKa3 and everything is the same. Again, I'll do one as an example. That'd be PA at, let's see if I can get this one right. At 840. At 840 mils, so that's 40 mils into region 3. We have pH is equal to I can keep my pen colors the same. That pKa, which was 6.19. And our increment just starts over 0.02s for our X. And our 0.2 stays the same. Dallas will tell me that that number is probably a little less than 6, 5.24. That low? I guess so. Somebody double check them on that one. That seemed low, but there's a reason why we're doing it. And then ditto. Go to the end. Okay. This is looking like it's glorious here. I guess let's go ahead and do the over titrations. And then we'll go ahead and plot this. So the over titrations. Remember, now OH minus will dominate once again. I have to move that because the chat thing's in my way. So at 1300 mils, at 1300 mils, remember, we're 100 mils over, which means we've only added 100 mils of our base to this now neutralized solution. So we say we have 0.5 molar sodium hydroxide per liter of sodium hydroxide. We are now just 100 mils, so 0.1 liters into that region. To be completely thorough, 1 mole of NaOH. is 1 mole of OH minus. And our new volume, right? This is the total volume. Is how much?
1.3.
1.5. How did I get 1.5?
Because you added two, I don't know.
Come on, Chef. You know how to do it. We had 100 mils to begin with, right? Wait, is it 15 or 14? Hold on. Let's go back to our chart.
15.
Oh, we're at 14. Sorry. 100 mils to begin with. 1,200 to get to the end. So that's 13 plus the 100 mils that we just went over is 14. I apologize for that. I can't do math now. So it's 1.4. Okay, so that will end up giving me a concentration of OH minus equal to 0.0357, which will end up with a pH equal to 12.55. Now we can do this at 14 and 1500. Now 200 mils over. So everything else up there will stay the same. We'll just change the volume of NaOH and the volume of solution. Those are just going to go up by another 100 mils each. Oops. There we go. So now is 0.5 moles per liter of the NaOH. We're now at 0.2 liters of the NaOH. We know it's 1 mole of NaOH, 1 mole of OH minus, and our new volume is 1.5 liters of the solution. OH minus there now becomes 0.0667, 0.0667, which will give my pH equal to 12.82. And so at 1,500 mils, we're now 300 mils over. And everything here looks the same, guys. This should be basically busy work at this point, but I'm going to go ahead and finish the busy work. .5 moles of sodium hydroxide per liter of sodium hydroxide. 0.3 liters now of sodium hydroxide. And again, our 1-to-1 ratio. I always like putting this just to keep reminding myself, why is my kid outside getting in the back door by using the combination? Because he can. Oh man. How does a 3-year-old watch you figure out the key code combination and walk in the back door all by himself? Telling you, man. Utica, tell him kids are ridiculously smart.
And they like to copy everything you do.
All right, OH is 09375, which will give us a pH is equal to 12.97. Notice that our pH is starting to slow down on its increase, and that's because we keep diluting. Brain doubles in size in the first year. Yeah, but he's 3 now. He should slow down. Oh, wait, that's right. Chad, you got kids, right? Now my kid is just opening and closing the door because he can. That's pretty funny. I can see him in the mirror from my office here. It's amusing. Yes, Chad, I agree. We are crazy at home. Again, it's kind of weird that like I can't just be with the people when I'm at home. It's kind of bad. I feel for everyone right now. We are all going cray-cray. All right. So Kimchi, I know you have all of these. So I need you to call them out so I can fill it in.
Okay.
40.
2.19, 2.55, 2.78, and 2.97.
3.5.
3.33, 3.52, 3.75, 4.10, and then 3.82, 4.17, 4.40, 4.59, and then 4.95. Okay, 5.14, 5.37, 5.72, and then 5.48, 5.24.
That one dropped down again.
Yeah.
Okay.
5.59, 5.82, 6.01, 6.37, 6.56, 6.79, 7.14, 12.55, 12.82, and 13.20.
I had 12.97. What would you have?
I
I'm gonna
had
use my numbers.
18. I copied.
Unless somebody got me unless I did it wrong.
Oh, let's see.
I know, we're getting there. Was that you, Dallas?
No, I wrote on it because I'm
Oh, it
confused.
is 12.82.
Who is that? Who is that screaming at me?
Low band.
Hello, man. Oh, look, what do you mean? There's nothing wrong with what you just wrote. Look at that. They all go up. I don't know what you're talking about. Yeah, so let's talk about that. I'll go ahead and yeah, you erase it, and I'm gonna point out here with, I don't know, do I have another color? Can I do this? Ooh, I can add a pencil or no? Ooh, what's a pencil do? No, I don't want that. Let's add another pen. Oh, and we'll make it
Rainbow.
Of course, you guys got rainbow. You want to know what is happening here, and you want to know what's happening. Where else did it go weird? You want to know what's happening there, right?
Yeah.
So the question is, what is happening here and here? So let's plot it, and then we'll sort of talk about that, because yeah, you're going like, wait a second, it's not doing what it should do, and that is correct. Hey. Erase. Okay, so let's go down. Let's make a cool plot. Oh, apparently I'm making it in rainbow speak here. Okay, so we know that this is going to be pH. We know that this is going to be volume of the base. And man, did we just make our lives fun. We have to go by 40s. Whew. Well, I could probably do this. We know that we're going to end at what, 4, 8, and 12? Let's undo that. 4, 8, 12, 13, 14, 15. Okay, so that means our midway point here. Get our midways. So this is 400, 800, 1200, 1500. And we went by 40s. That's 20, so I need 40, 80, 120, 160. So I need 4 on each side. Ooh. Should I do this in Excel real quick? Is it that button? Let's go Excel. This will be hard because I don't have my thing up. So if I do this, let's go volume base in, let's be clear, in mils, and we'll do pH. I'll do those. I'll double click. No, I won't. I'll grab my handy dandy mouse because I remembered I had a mouse. All right, volume of base. This is going to go with 0, 40, 80. And we're going to go ahead and drag that down until we get to 1200. And then we'll do 1300. 1400 and 1500. All right, Chattamaru. Let's just do this. We'll make it nice and centered. Our pH. Kimchi, read them off again. 1.97?
1.42.
1.42.
Then 2.19. 2.55. 2.78. 2.97. 3.15. 3.33. 3.52. 3.75. 4.10. 3.96. 3.82. 4.17. 4.40. 4.59. 4.77. 4.95. 5.14. 5.37. 5.72. 5.48. 5.24. 5.59.
Oops, hold on. Shoot, 5.24, 5.59.
Yeah. 5.82. 6.01. 6.19. 6.37. 6.56. 6.79. 7.14. 6.69. 12.55.
Wait, I don't like that.
That's the over.
So it can't be 7.14.
Oh, sorry, 9.96. 9.69. There you
Okay.
go. 12.55, 12.82, and 13.20.
12.97 is what I had. Thank you.
Oh.
Unless somebody's got a 1302 to back her up.
Did I get it wrong?
Okay.
Oh, I did get it wrong.
Okay, so let's take a look at this. We do see that we have an issue here right around those midpoints, right? Now, it turns out that right near these equivalence points on this, you end up with a situation where it starts to vacillate. And if you go back to the equilibrium constants, I mean, for Pete's sakes, look at them. They're almost on top of each other. 10 to the negative 4, 10 to the negative 5, 10 to the negative 7. Most of the times when we're looking at a diprotic, these things are widely spaced apart so that you can get a really good curve out of it because they're like 10,000 units apart. These are 1,000 or 2,000 apart. They really start to essentially interfere with one another. One midway point is starting to interfere with the other midway point because they're only off by a factor of 10. And so there gets to be a competitive effect when you start reaching these midway points and then the end points. So what we can see, and let's see, I don't know if you can see my mouse. Can you guys see my mouse?
Mm-hmm.
Okay, so everything looks pretty good until you get to the end point. Well, one person's, I wonder if I can actually draw on this. Can I draw on this? No, okay. Wait, no, I can. Hold on. Draw. So
You can draw on it or you can move it over to your OneNote.
Oh, I can?
Yeah, you just copy and paste it.
Well, shoot. Let's do that. Let's go back to OneNote. Now let's paste it, and then we'll get rid of everything else. Did that do it? Hey, there it is. All right, so let me just erase this thing real quick. Sorry about the dead air, guys. I feel like I'm on radio right now. How do I pick you up and move you? I guess this tool, right? All right. Let me just move it again, and then I bet Boudica is going to say that I can expand it out.
Yep.
By clicking and dragging like so. Oh, right. So here we have, is that the correct place for our midpoints? 2, 6, and 1,000?
Mm-hmm.
Yeah. So what ends up happening is both of those start really messing with the endpoint because both of those midway points basically get into a competitive effect with each other when they do this. And so basically both are fighting over what's going to happen at that endpoint. And because they are so close, they basically have equal power over each other. When we did our diprotics, those KAs were so far apart that they basically never saw each other as you reached an endpoint. You'll also notice, by the way, that look at the slopes of each of these buffer regions. They're not very flat, right? They're actually increasing rather quickly. And that's because since they're so, since they're basically so close to each other and so on top of one another, they don't have very long to establish a good buffer region, unless of course you did a lot. Now I made this problem in such a way that we do have a lot of base to have to add to try to stretch those buffer regions out. But if I had done like a standard, like, oh, I'm just gonna titrate this 2 molar with a 1 molar, basically this would almost make a ramped up linear plot to the endpoint. If I really wanted to stretch it out some more, I might have wanted to do a 0.1 molar sodium hydroxide, such that as I'm trying to neutralize this, as I'm trying to move that pH, if I'm doing it slowly enough, I could probably get better plateauing in between on those buffers, but that would be a ridiculous number of points to try to get that curve. So I balanced time versus demonstration here. So again, you know, if when you get to those triprotics, because a lot of those Ka values are so close, they do start interfering with each other as you get closer to the individual endpoints there. Now, toward the back end over here, though, we can see that definitely looks like what we expected it to look like, with our very end point, you know, lying where it should, because there's nothing on the back end to interfere. What does vacillate mean? To go back and forth. I want to draw a better thing. Okay, so at the end of the day, I know this was a long thing here. At the end of the day, what I wanted to point out though is, yes, all of the steps are essentially the same. And we should have no problem with this. And I truly hope in some respects you guys were bored, right? Yes, we've done this. Yes, we know how to do this. Yes, we get it. But there was one last reason why, is to show you that when you get to these more complex triprotics and their Ka values getting really, really close, it becomes very difficult to get what I would like to call a clean plot like we've had in previous lectures, because those Ka values are really so close. I want to do one last thing here before we take off. And that is, I want to show you a little note on the indicators, and also what happens when you add one drop into your titrations, such that we sort of understand here what's going on. Quick note. Oh, can I write a little bit better there? So, quick note on indicators. Okay, let's take bromothymol blue. And I'm just going to do it as H indicator, going back and forth to make H plus and indicator minus, because this is what these indicators are doing. They have the ability to either suck up H pluses or spit them off. Usually, since we're titrating an acid with a base, we're watching that base actually end up killing one of the H's on an indicator. If you were to look up the structure of bromothymol blue, you would find that it has a whole bunch of ring structures on it. And as we'll get to with, well, actually we did that with the MO theory in Chem 120. The MO theory allows electrons to jump those band gaps. We saw that with the transition metals, but it also does this with the pi orbitals of ringed structures. Depending on how many rings you have and how they're connected, they'll be able to absorb a different wavelength based on the, quote, length of that whole pi bond interactions and the such. When you actually end up getting one of those OHs to attack and rip off one of the H's, what you'll end up doing is breaking that chain, shortening that loop, and therefore making a different color. Now, with bromothymol blue, we know that it started out as yellow, and it would turn into blue when you ended up getting a bunch of those indicators floating around in there. If we wrote the KEQ for this, we would say it's the concentration of H plus times the concentration of indicator minus all over the concentration of H indicator. what happens when we get to the midpoint or the equivalence point? At the midpoint or the equivalence, we know that if we're halfway through trying to make this indicator change from yellow to blue, and some of you saw this when you did the indicators, you saw that neutral water was green. So you have, you basically have everything as part blue and part yellow because it dissociated equally. So at the midpoint though, when you're trying to go through this, you know that the concentration of the indicator, H indicator, is equal to the concentration of indicator minus, which means that the pH is equal to the pKa for bromothymol blue. Now, this is actually the point where it's switching. This is the point when it actually switches from one color to another. Now, indicators switch at pH equals their pKa. And it turns out for bromothymol blue, it's actually right around the 10 to the minus 7, or the pH is 7. But here's the funny thing. Because that's where they switch, this is why we always choose an indicator that switches just after we want to be neutralized. Why do we want to choose it after we were neutralized? Well, if you think, go ahead, yeah.
Because if it changes, then you know you've gone over that point.
Right. If it actually truly changes, we know we're done. Okay, guys, what's one of the big errors that we always kept saying in Chem 110 over and over and over? What's one thing we could always count on that we could write down as an error in our data?
How pink is pink.
Exactly, how pink is pink. So my question is, if we're going from yellow to blue, how green is green? Right? So if we are going, if we are going from yellow to blue, how green is green? We don't want that ambiguity, so we know the difference between yellow and blue. We do not want that ambiguity. So we keep it yellow versus blue. We know that difference. We know that difference. Okay, so we always choose an indicator that switches just after we want to be done. So if you want to completely neutralize something, think about your vinegar and your sodium hydroxide. That will essentially be done at pH 7. We chose phenolphthalein. Well, phenolphthalein switches at 8.3. So technically we've overdone it, yes?
Yeah.
Yeah. We don't choose bromothiamyl blue because bromothiamyl blue would be like, is that green yet? Or is that yellowish? Or is it, oh, I don't know. We don't do that because we want it to do its thing. And we want it to be drastic and we want to say, boom, you are done. Stop. Now, I just want to point out, we always choose one that goes afterward. Everyone always goes, well, then you're not neutralized. Well, yeah, you've gone over. Yeah, and you've always gone over the exact same amount. But let's analyze, what does that mean to go over? So, what does it mean to, I'll just say go over. Go over in a titration, all right? We always know, we get to that end, and we have that one drop, and Lion Lee freaks out because it turned that deep magenta, and he's like, FML, okay? And I always tell everyone, from 110 on, stop the insanity. Watch this. Typical titration. Typical titration uses 0.1 molar NaOH and maybe 50 mils total solution. All right, you've got like 10 or 15 mils of the stuff you're titrating. You'll use 35 to 40 mils to titrate it. You got about 50 mils of solution, okay? Well, what does that look like? Let's go one drop over neutralized. One drop is approximately 0.05 mils. There's about 20 drops per mil. Drops per mil. Okay. So let's take 0.1 moles of sodium hydroxide per liter of sodium hydroxide. And let's add that to the 0.1234, is that 4 zeros and a 5? Yeah. Oh, and that's going to be of the sodium hydroxide. Okay. And of course, we know 1 mole of sodium hydroxide is equal to 1 mole of OH minus, and that is now into 0.05, 1, 2, 3, 1, 2, 3, 4. So 0.005 liters of solution. So I got the 1 drop into my 50 mils. Dallas, what is my concentration of OH minus? Can we agree that that's essentially 1 times 10 to the minus 4? And I know you're going to go, no, it's 0.9999, whatever. I'm going to do the approximation there. This means that the concentration of H plus is equal to 1 times 10 to the minus 10, or that the pH is equal to 10. One drop, oh, can I write? I'm so antsy my pantsy to show you this. 1 drop over jumps the pH 3 steps. Okay, 1 drop. So this means we will definitely see this, the shift. We will definitely see the shift in the indicator. While doing just about nothing to the titration volume. While doing nothing to the titration volume. So that's why in Chem 110, Chem 120, we're titrating, and someone's like, oh my gosh, I can't believe this, just one drop. Oh, my data is crap. And I'm like, no, it's not. Because one drop does nothing. 0.1%. No, it doesn't do anything to the value that you would have recorded as how much it takes to neutralize. But we do that because once you've neutralized something and you add just that one more drop, it can significantly jump the pH of that solution. I thought that was kind of cool. First time I did that calculation, I'm like, whoa. I mean, I expected it to move, but not like that. All right, that's as far as I want to go today. Did anybody stick around?
Yeah.
Okay.
Yeah.
All right, I'm going to go back to all of us here. Did we have any questions before I go ahead and stop this and go get some lunch and then come back at 1 for some office hours? Or stick around after I grab a cup of coffee? All right.
I'm all good over here.
You're all good? Okay. I'm going to go ahead and stop the recording.